Hello everyone and welcome to Rust Planet. I'm Akshay Arunachalam and today I'm going to be talking about the Shakthi-RISCV-HAL. The Shakthi-RISCV-HAL is a crate written in Rust to provide the functionality of an hardware abstraction layer for the Shakti processor. The Shakti processor is a groundbreaking development in RISC-V architecture by the RISE lab at IIT Madras. It has a visionary roadmap for diverse market segments. Shakti unveils its initial offerings, the E and C classes. It's tailored for IoT, embedded systems, and desktop markets. The Shakthi-RISC-V-HAL is written specifically for the C-class processors. These processors feature royalty-free and open-source attributes under the BSD3 license. The C-class, or written Exploring Vajra, is an order a 6-stage 64-bit microcontroller which supports the entire RISC-V ISA, targeting mid-range compute systems with a variable frequency range of 200 to 800 MHz. It is customizable for both low power and high performance variants. Operating systems such as Linux, SEL4, and FreeRTOS have been successfully ported and verified with the C class. The Vajra, which is the C64A100 in the C class, is a single-chip 64-bit microcontroller aimed at mid-range applications, workloads in industrial controllers, and the desktop market. Today, we'll be using Rust in the Shakti processor, which brings several advantages aligning with Rust's strengths in system programming and embedded development. Rust in general, as opposed to C, has many memory benefits, or general benefits as well. There's memory safety, zero-cost abstraction, concurrency and parallelism, static typing, community and ecosystem, cross-platform development, and open source and transparency. You can further look into why Rust is more beneficial as opposed to C, but today I'm assuming you already know how awesome Rust can be. Now coming back to the Shakthi-RISC-V-HAL. This here is the GitHub page for the Shakthi-RISC-V-HAL. As you can see, there is examples, the source file, and many other required files for running any sort of Rust project. There's also a very small README about the project. The Shakti processor is an open source initiative developed by the IIT Madras, and also shows you how to actually use this HAL or how to use this GitHub page. This can be done using the Shakti Rust book, which, as you can see, is a Rust book or book which is written to show how exactly to use the HAL. So inside the HAL, we've mentioned all the important or necessary protocols to use for any sort of standard board. You can see that these are all the possible protocols that we've exactly written to access any sort of GPIO pins or any registers or etc. which are there on the board. We have the standard UART, SPI, the GPIO, the I2C protocols. Today's intention or the reason of making this video is not just to showcase the HAL that we've written, but also sort of write a small code or a blinky code to actually show you how to use this HAL and how leveraging everything that's written over here is actually beneficial, especially if you want to run Rust in any of the Shakti processors. Now, before I actually go into writing this blinky code or writing any sort of code, let's actually look at the Rust book and see what it tells us about the board and sort of gives you an introduction on what exactly are we doing and what this board is for. So we have a small introduction about what Shakti is, how Rust is written in the Shakti processor. We have some more information about the actual hardware that is being used for the specific board. So the board that we are actually using is the RTE7, which is the RTX 7 100T FPGA board. As we know, FPGA boards are essentially programmable boards which try to emulate a specific type of architecture or processor that's there in it. So it's exactly this is sort of the architecture. This is the board that we're actually going to be working with. It's not really bound to like any sort of single set of peripherals. It has a lot of different UARTs, SPIs, I2Cs, etc. There's a few more features about the board, about the actual like clock speed and the ADC, about what that's there, the system features about the flash and etc. One thing you'll have to mention or remember in this is that there are 4 LEDs because we are going to be dealing with the blinky code over here. So we have 4 LEDs, there's 4 RGB LEDs. And then there's also an external flash with which we're working with. There's also more references to any of these to any of the further information about the board itself. We also talk about the no standard platform, or basically any sort of application which is written at the crate level in Rust. You use a no standard, because no standard essentially means that you are in a resource constrained environment, since we're dealing with embedded system devices. So we don't really have the regular or normal standard environment. This again is more about Rust itself. Why are we using it exactly in Shakti? Like I mentioned before, we have memory safety, zero cost abstractions, etc. If you want to know more about exactly what each point talks about, I'll be putting the link to this book in the description. So we also have a little paragraph about why not C. Why Rust? Why not C? I mean, C is a standard programming language, but as you can see, we've actually listed out many advantages of Rust over C. We also have the tooling, which just is essentially how are we flashing, or how are we exactly running the code from from the laptop onto the board. So we are actually using OpenOCD. We're using GDB as the debugger. OpenOCD is actually used to form the connection or a bridge between the GDB and your debugging hardware. You'll also need your standard Rust up, your nightly versions of Rust, etc. So these are exactly what you need to run the code on or flash it inside of your board. But of course, the first step before, in general, when dealing with FPGAs, is to first burn or flash your like bitcode onto the actual board. So you need to know what board you're trying to emulate. So that's done during or through Vivado. So you just have to download Vivado. You have to run and follow these steps. They essentially tell you how to like make or emulate the actual Shakti processor on this specific RT7 board. And this here is some more standard information about the actual peripherals which are present on the board. So there are other types of classes with which Shakti works with, but the one we are essentially working with is the C class. The 64-bit C class, 6-stage microcontroller, has the entire RISC-V instruction set, and then other information about the boards themselves. What's important to us is the actual peripherals which are present, your GPIO pins, your counter, your SPI UART, your I2C, etc. So today I'm going to be working essentially with our GPIO pins. That's, I think, the most important thing right now, because I'm just going to be writing a Blinky level code just to showcase how to run or flash your Rust in the board. So the GPIO functionality in this processor is very versatile, but there are certain things you need to know before you can dive into any sort of coding in this. So in GPIO, you have the registers. There are essentially two types of registers that are very important to remember. You have your direction register and your data register. Your direction register essentially configures the GPIO pin as either your input register or your output register. And then you also have your data register, which essentially should be having some input. It can have either an input data from the GPIO or output data with GPIO, and it has accessible of 1 byte, 2 byte, or 4 byte sizes. So in the code which I will be opening up, we'll be talking about the direction control and the actual data register. So the direction register and the data register. And the general sequence is that you first write into the direction to say, hey, I want to do some input or output, and then just write the value into it. So this is a small code written to implement this functionality, which I will be showing you properly in the code. There's also other things like talk registers, which is a specific crate that we are actually using to, which is we're importing from a specific library to represent your registers. Because the code, we usually write registers like talk registers is like an abstraction. It essentially makes it way easier to deal with registers than actually going into specific detail about it. And then we have other information like your bit fields, your wrappers, etc. So now let me open up the code and actually show you how this looks, how this GPIO functionality was written in Rust. And so here it is. This is the code which we have written. I've just opened this up on VS Code, so it's a lot easier to look at, I guess. It's a lot easier on the eyes than just a white screen. So this is the GPIO GPIO crate or GPIO Rust file that deals with exactly what I had talked about before. So we had just have like general functionality here. So we have these RISC-V block registers, which are registers used to abstract this whole functionality. We have your interfaces, your bit fields, your register struct, and you have your read-only, write-only, or read-write-only registers. So this is essentially the mode in which you deal with any of these pins. So any of the pins in general with GPIO, you don't really want to keep it just read or just write. You want to stick to read write. So I'm assuming anyone watching this has some level of expertise or some level of experience with Rust, because going into what each thing means, I guess will take a little bit more time. So if you don't exactly know too much about Rust, you can, I think, go through a bit of the Rust book and kind of understand what each line does. But I will give you a general idea of what was written here. So you have like your talk registers, and then you actually have the definition part, which is used for the GPIO parts. So we have the base address of the actual GPIO peripheral. These values or constants have already been defined in the datasheet of the a datasheet of the given board. So this was sort of we worked with them, IIT Madras, to kind of figure out what each or where each thing resides in. So we have the register struct, we have the register blocks where we have defined our the direction register, then the data register. Then we actually have the values inside of it, which we're trying to say, hey, can I have a 32-bit for the direction register, 32-bit for the clock line or like the data register, and I want to also have this offset. We've also define the registers with an MMI or DREF wrapper. This is also sort of essentially you're trying to get into. Actually, let me just show you the definition of this. So this one's a little bit of more of a complex topic, and actually takes a lot more knowledge on Rust rather than embedded or the Shakti thing itself. So this just talks about the MMI DREF wrapper. It's essentially a wrapper that is used to access or dereference any of the information or any sort of data which is present inside the hardware itself. So this I think we can cover for another video. So this is sort of a bit more of an interesting topic, talking about this deref wrapper functionality. So now coming back to this, we've also defined our public struct of GPIO winner. We've defined the registers of type register. And now we are going into the initialization. So we first initialize our registers with a new value. And then we have the two different functions which actually matter, the set direction control and the set data register. The direction control as I've written is a function which essentially sets the value as either input or output. So it's a high or low. And the same thing with our data register, which either has it as any sort of value that you want to put in because it's data. So it's the value that you want to set inside of the data itself. So this is like that's about it. It's pretty simple, I think, as opposed to anything complex. This kind of gets the job done very simply. So now that we've sort of looked at what the GPIO crate is, I'm going to be writing the Blinky code and show you how exactly to use this RISC-V-HAL. Okay, so I've made a source file for GPIO applications, inside which I'm going to be writing the main RS file for this specific. Let me get rid of this. We don't really need this. Yep. Yeah. So we're going to be writing the main file. This is the application where we are going to be writing our Blinky code for this code. So now I just need to include all of the the RISC-V crates or whatever crates that I actually need to be writing this code. Yeah, we have the ASM in which we have our delay, and then we also have the delay, which I will be mentioning. Then we have our RISC-V RT, which is another crate that is used for sort of I don't know, entry, I guess, like used for the entry point because we're not using a standard environment. So we will be requiring this for the entry point, and then we're actually using our Shakthi-RISCV-HAL, which I'll log in Shakthi-RISCV, the Shakthi RISC-V-HAL, which is the GPIO. point, and then we have our GPIO inner, and then our offset. So we have the inner, and then we have the GPIO offset. So one second, we'll put a 5 yeah. Now we are going to be writing, we're going to be using the constants that I have defined here. These are just constants about which each GPIO pin is with what register. So this is just like a standard already defined thing. So we just have on mod the GPIO constants because we are including it in this file, and then we have we're actually using these GPIO constants. We're using all of it. Yes. Yeah. Now we've done all this, so now let's go into writing what each LED is dealing with each pin. So what each pin is dealing with which LED. Yeah. So I think first let's define first one. So we, like I mentioned before, there are two RGB LEDs, and then there's two other LEDs. So we have the LED R, which I think is the GPIO. Let's see here, GPIO 16. And then we have the other LEDs, which are also, which I will be defining now. The LED 0. So, okay. Okay, so these are all the different pins which are associated with each one of the LEDs. Next, we're going to be talking about the actual direction control register and our data register, which is there. So we have the GPIO, let's call it the GPIO direction control register, and which has an address of 000. Then we have the const of your GPIO data register. Data register, which has a value of 0x08 addressing. Okay, and then we're going to be on our other constants. We're having a delay because we're going to be flashing the LED, so it's a bit of a delay here. So we just have our delay 1, which has a value of 1000, and then we have our const delay 2, which has a value of 1000 again. Okay, so we've defined all of the different constants essentially. Now let's actually get into the meat of it. Let's actually go into the definitions which are there inside of the crate. So now I'm going into the GPIO. Now I'm going to have this value of, I'm assigning this GPIO value inner. Okay, now let's make an implementation, also called GPIO access, inside which we'll be making a function. We'll make a public function, making a new instance of this GPIO access. One second, I'll just put the screen down. Yeah. Which will be returning back your GPIO access. Inside the function, we're going to be having the GPIO access, which will have a type GPIO, which will unsafe implementation of the GPIO inner I will be calling the GPIO offset. Okay. Now inside the implementation, we're going to be actually having your two functionality, or the two functions which are mostly important. I mean, the only two important functions, which is your turn on LED function, where you'll have a mute. Basically, you're having a self reference inside the implementation and the actual LED value. And then you will have your turn off LED, which will just turn off all the LEDs which are present inside. So the only thing needed is the self argument. Now inside of it, we're going to be having using this LED. So we have the actual GPIO, and then we're calling into the set data register function, which is there inside of the declaration of it. We're calling this LED. And then inside the turn off LED, we have the turn off LED. We're just going to be setting all of the data registers present inside of it as 0. Sorry, and we want the GPI first. And then we have the set data register. And then making everything 0. Yeah, okay. Then we also have now the direction. So this is just turning on and off the LED. But we also need to set the direction. We also actually have like a set direction function. So again, we have the pub function, set direction. Then you have your self mute. Now we'll be having the value with which we're going to be setting a specific direction to. And then in this one here, we again have the self.gpio dot your set direction control, where we're passing this value inside of it. Oops. Come on, value inside of it. Now we've defined all the different functions that are present. So now let's actually go into the function. We're going to write the main, which is but before that, we need to have our entry, because we're using the RISC-V entry. And then now let's have our main. And then we have our main, within which we're going to be writing. So now let's actually get onto the main function here. So we're going to have to declare our GPIO starting address, especially of the memory MMIO start address, which has it as 0. It's 1000. And then we are going to be having our access from this specific to the GPIO access structure. So we're going to have the actual access over here. So we have the GPIO access. We're going to be making a new instance of it. So we're just going to go new here. Then we're going to be setting a direction, and then we're going to first turn off all the LEDs. So we're just going to have GPIO access. We're going to have the set direction, and then we're going to be calling all the LEDs that we have. So we have LED B or LED G. Okay, so now all the directions have been set for every one of the LEDs. We're just gonna, for extra measure, just turn off all the let's turn off all the LEDs. Turn off LEDs. Now we're going to set go into each one. So now we're gonna run a loop, and we're constantly going to turn off, turn on, turn off, turn on all the LEDs. So we're just gonna write a loop here. And inside of it, we're going to have some function. We're going to delay loop. Delay loop, inside which we're going to be passing our delay 1 and delay 2. Now let's actually turn off and turn on our LEDs. So I'm just going to write the logic here for this. You don't need to see me type all this out. So all the functionality is written in. This just essentially turns on all the LEDs and turns off the LEDs. So you can write this in any way that you want to write it. But the only thing that's left to actually do is to write the delay loop function, which we had not mentioned before. So let me just write that function over here. This is just a very simple logic. It's just running a a loop again, but this time you're just having a while loop, and then we'll be declaring each variable. I'm just going to take in our delay value. So we're going to have 2 here, control 1, control 2, and then we're going to have, I'm sorry, yeah, let me just mention the data type. U32, and then we're just going to mention this here too, U32. Yeah. So inside the function, we're just going to have a while loop that's running. So we're going to have control 1, which will say until this is greater than 0. Let's have our temporary temp control, which will be the same exact value as control 2. Then as long as temp control is greater than 0, we're just going to run, we're going to keep subtracting temp control -1. Sorry, minus equal to 1. Okay. Yeah. And then we're also going to have control 1 subtracting its value minus equal to 1 here. Yeah. Okay, this is this while loop. Yeah, okay. So this is just the normal function that we've written here. And then one last thing to mention over here is actually your panic handler. So panic handler is usually needed in Rust or when dealing with any sort of embedded this thing, because it deals with any sort of problems that are present in the code. So inside the panic handler, we just have a normal panic function that is mentioned here. So yeah, the underscore we have our panic handler, panic info. So we're gonna return back our exclamation point, and then we're just gonna run a loop inside of it once again, which has the nope RISC-V ASM nope function. Yeah, okay. So now we've written all the required functions, we've written everything. So let's actually compile this, check it out, and then flash it onto the board. Now all I have to do is just run it, cargo build. Yeah, and it has been compiled successfully. So now I will be flashing it on the board, and I will now show you the blinking LEDs. So that's about it. That was the basic Blinky level code. If you want more information or you want to see more about it, I will be putting down the link of this HAL crate on GitHub. I'll be putting it in the description, and I'll also be mentioning the book, which is also mentioned inside the RISC-V HAL repo itself. So that's about it. Thank you so much for watching. If you have any doubts, please do comment down below. Make sure you like the video and subscribe. Thank you.